Section 1.6 on Achieve deals with exponential and logarithmic functions. Pretty straightforward for most of the problems. Take a look with me at the first one here. It gives you an exponential base e on both sides of the equation. You know, if that's the case, then the only way that this equation could be true is if the exponents are equal to one another. So I just went ahead and set my exponents equal to one another. 4x is equal to 2x plus 8. Subtract 2x on each side, we get 2x is equal to 8. Divide by 2 for x is 4. And that's the only thing I had to enter into the answer blank on Achieve, just x equals 4, and it was fortunately correct. Now, I like the second one better here because instead of just giving us the simple case where the bases are already the same, the bases are not the same, but we can work to get them to be the same. So if I have 6 to the x is equal to 1/6 raised to the x plus 5 power, what I did there is I just thought, well, 1/6 is the same thing as 6 raised to the negative 1 power. And if I have 6 raised to the negative 1 power raised to the x plus 5 power, power to a power rule says simply multiply those exponents. So that gave me 6 to the negative 1 times the group x plus 5. That's where this 6 to the negative x minus 5 came from. I just multiplied a negative 1 through there since this was to the negative 1 power. Now, once I get that, all I have to do is set my exponents equal to one another, because the only way these bases to these powers can be the same is if those powers are the same. So x is equal to negative x plus 5. We add x to both sides to get 2x is equal to negative 5. Thus, x is equal to negative 5 over 2. And that's what you do. For the third one here, similar, we have 9 to the negative x power is equal to 3 raised to the x plus 5 power. Okay, so whenever I'm trying to figure that one out, I would just go in and say, well, all right, I need to get the same base. Instead of trying to manipulate the base of 3, I can easily manipulate the base of 9, because 9 is the same thing as 3 squared. Now, when I say 9 is the same thing as 3 squared, I can say, well, 3 squared raised to the negative x, power to a power I just multiply. The left-hand side is the same thing as 3 to the negative 2x power. And I know that that has to equal 3 to the x plus 5 power. So now I get negative 2x has to equal x plus 5. And I can say, well, if negative 2x is equal to x plus 5, then I'll go ahead and subtract out x on each side and get negative 3x is equal to 5, which yields in a solution of negative 5/3. Now, instead of going on to each problem on here, I think I'm just going to maximize the screen to make this appear larger. Your next problem, or my next problem on Achieve, and yours will be similar, was x to the 3 over 2 power is equal to 729. Well, you know, if you're trying to solve for x in this problem, then the only way to get rid of the exponent 3 over 2 is to raise both sides to the 2/3 power. X to the 3 over 2 raised to the 2/3 is just x. But then we have 729 to the 2/3 power. You could use a calculator at this point, but you really shouldn't need to on this one. What I did is I just said, well, we know that the 2/3 power means that we need to take the cube root of 729 and then square that answer. Cube root of 729, I thought, well, 9 times 9 is 81. 81 times 9 is 729. So the cube root of 729 is 9, but then I need to square that answer. Well, 9 squared is 81. Glorious final answer there, the 81. Then the next several questions are pretty quick and easy. What I'm wanting you to remember with logarithms, please remember, all a logarithm is asking you is, what number do I need to raise the base of that logarithm to get the term inside the logarithm? So the log base 4 of 16, it's literally asking you, what power do you have to raise 4 to in order to get a 16? And I accidentally just said it, 4 2. I have to raise 4 to the second power to get 16. So since 4 squared is 16, the log base 4 of 16 is 2. Now, You could have also just said, well, log base 4 and exponential base 4 are inverses. So you could have rewritten 16 with a 4 to the second, and then log 4 exponential 4 would cancel and leave you the 2. The next one is the natural log of e to the 46th. And you know natural log is the log base e. So log base e of exponential base e cancel out, and you're just left with the 46. Or this is literally asking you, what power do I need to raise e to get e to the 46th? And your answer is 46 that way. That helps us out with number 7, log base 12 of 12 to the 8th. This is literally asking you, what power do you need to raise a 12 to get 12 to the 8th power? Well, clearly the answer is 8. Log base 12 of exponential base 12 to the 8th, 8. So the next question, number 8, is also really easy because natural log and exponential base e eliminate one another. So this whole function is just a 7 plus an 8 plus a 9, and we get 7 plus 8 plus 9. Well, 7 plus 8 is 15, plus 9 is 24. Now, for the next one, over here, I'm wanting you to understand the log, the natural log and e are inverse functions, so they cancel each other out. The log base 12 and exponential base 12 are inverse functions, so they cancel out and leave you with that 8 there. In the same manner, exponential base 2 and log base 2, they're inverse functions. They cancel each other out. So exponential base 2, log base 2 counteract each other, and now you're just left with the answer of 9. Number 9 has an answer of 9 on mine. Now, 10, a little bit trickier. I loved it. So unlike 9, where you could just immediately cancel the exponential base 2 and the log base 2 and have your answer of 9, in 10, that's not the case. And I don't see anything here initially that can easily cancel out. But here's what you do. You're supposed to remember one of the rules for condensing logarithms says that any coefficient of a logarithm can be raised up into the exponent of the term within the logarithm. Well, then when you do that, you can say, well, all right, this is the 11 raised to the log base 324 of 18 to the second power. 18 to the second power conveniently is 324. So you say, well, 18 to the second is 324. How does that help? Because then you can say this log base 324 of 324, this is literally asking you, what power do you need to raise a 324 to in order to get a 324? Well, clearly it's the first power of 324. So the log base 324 of 324 is just a 1, and we get the whole exponent simplifies to be a 1. So we get 11 to the first power, which is just 11. Then after that, you got into equations that you had to simplify. So 11 is going to give you an equation with natural logs. What you need to remember is to condense down as far as you can on each side. Condensed mine on the left-hand side, the natural log of 2 minus 3x minus 2 natural log of x. First of all, you're supposed to remember anytime you subtract, it's going to be the positive, the term with the positive log, that term goes in the numerator, the minus goes in the denominator. You're going to divide by whatever you subtract. But then you can also remember here that 2 coefficient needs to be brought up as an exponent on that x. So this becomes the natural log of 2x minus 3 divided by x to the second power. And then I can say, okay, once I do that, I left the right-hand side alone. Now I have the same logarithmic base. So the only way the left-hand side could equal the right is if what's inside of these natural logs equal each other. So that's what I've done. 2 minus 3x over x squared is equal to 2. We multiply both sides by x squared. We get 2 minus 3x is equal to 2x squared. The instant I see that quadratic on the right, I go ahead and move everything over with it. I add 3x, I subtract 2. So now I have 2x squared plus 3x minus 2 is equal to 0. I'm thinking that this one should factor pretty nicely. So what I did is I just said, the only way I can get a 2x squared for the first term is a 2x and an x. Now the last term needs to multiply to be a negative 2. But I know that my middle has to sum to be 3. So I'm thinking, well, hey, 2 times 2 is going to give me a 4x. And then if I put a minus 1 here, that'll be a minus 1x. I'll get plus 4x minus 1x for my total of plus 3x. It's going to factor to be 2x minus 1 and x plus 2. Now, when you use the zero product property to set each of these factors equal to 0 and solve for x, if 2x minus 1 is 0, then 2x is going to equal positive 1, and x equals positive 1/2. If x plus 2 is equal to 0, then x is equal to negative 2. Now, both of those are legitimate answers we get through the algebra, but whenever you have a natural logarithmic equation, you should be highly suspicious of any answers. And why do I say that? Well, because you remember, the domain of a logarithm is only defined for positive values of x. The natural log of 0, undefined. The natural log of a negative number, undefined. So I can say anything that would cause the terms inside any of these logarithms to be negative cannot be an answer to this problem. So when I'm thinking, can 1/2 be an answer? I would get 2 minus 3 times 1/2, that's 2 minus 1.5, still positive. This one would be positive, so I can say that's okay. What about the negative 2? Absolutely not. It causes this logarithm to have a negative number on the inside, which is undefined, so I had to restrict that and say it's not in the domain of the problem. The one and only solution to this problem was x is equal to 1/2. Now, for number 12, 11 gave us a logarithmic equation, 12 gave us an exponential equation. Whether you're doing a logarithmic or an exponential equation, the first step of isolating the term is always the same. I need to get that exponential function by itself. I divide both sides by 29. Now I need to get rid of that exponential base e. Well, the inverse of exponential base e is natural log. I take the natural log of both sides. When I take the natural log on the left-hand side, the only thing remaining is just going to be that negative 7t. When I take the natural log on the right-hand side, I have the natural log of 4 over 29. So negative 7t is equal to this natural log, so t is going to equal that natural log divided by negative 7. And Achieve is wanting an exact answer here. I would just leave it like that. No need to go to your calculator and get an inferior decimal approximation to that. We want an exact answer there. Now, for the next problem here, for number 13, it gave me 6e to the negative 5x power is equal to 2. Similar to the last problem, first step is to get the exponential function by itself. Divide 6 on each side. 2 over 6, same thing as 1/3. So now we take the natural log of both sides, and you'll get negative 5x is equal to the natural log of 1/3. This is very, very similar to the last problem. And you can just say, well, now when you solve for x, you'll just be dividing by negative 5. So x is going to equal the natural log of 1/3 over a negative 5. Final answer there. For my next one, I get the natural log of x to the 9th minus the natural log of x squared is equal to 7. So back to a logarithmic equation. I know in logarithms I need to condense. Whenever I subtract, I'm going to divide their terms. Any term that's divided goes in the denominator. So this condenses to the natural log of x to the 9th over x squared, which you know you can then simplify and say, well, that's just x to the 7th inside of that natural log. Now, in order to get rid of the natural log on both sides, you need to exponentiate both sides with an exponential base e. When you do that on the left-hand side, e raised to the natural log cancel out, and you're just left with a term on the inside, the x to the 7th. But you need to put the right-hand side of the equation inside of an exponent base e as well. And so now you'll get x to the 7th is equal to e to the 7th. How can x to the 7th equal e to the 7th? Only if x is equal to e. So you could have said, well, what was he doing from this step to this step? You could say he's taking the 7th root of each side, or just recognizing that if the powers are the same, then the bases have to be the same. And that would be our final answer there. Now, when we look at 15, we have y is equal to e to the 4x minus 15. And in this one, it was asking us to find the inverse of this exponential expression. We know the inverse of an exponential is a logarithmic expression. So if I'm finding the inverse, I can say, okay, the way I find an inverse is I switch the x and y values and solve for the new y value. I switch the x and y values, solve for that new y value. How are you going to solve for an exponent? Well, you've got to get it out of the exponent by getting rid of that base e. How do you get rid of an exponential base e? You take the natural log of both sides. So from this step to this step, I'm taking the natural log of both sides. The natural log of x is equal to this exponent, 4y minus 15. Now I can solve for y by just saying, well, I'll add 15 to both sides and I'll get the natural log of x plus 15. Now, whenever there's multiple terms like this, it probably is better notation to close out your natural log to make sure it is very clear that that plus 15 is not inside your logarithmic function. So now I'll have the natural log of x plus 15 is equal to 4y. And so our solution for y, which is going to be our inverse function, f inverse of x is just the natural log of x plus 15 over 4. And then for the last problem here, we have our e to the 7t plus 5 is equal to 7 times e to the 5 minus t. Okay, so we have an exponential base e on both sides of the equation, but before we can even deal with that, well, we need to be able to get rid of, before we can deal with solving for the exponents, we need to get rid of those exponential bases. So the way you get rid of exponential base e is to take the natural log of both sides. Now, I take the natural log of the left, natural log of the right. There was a coefficient in front of that e that I'll have to address on that right-hand side. The left-hand side, really easy. The natural log and e eliminate one another, and you'll just have 7t plus 5. Now, the natural log and that e can't just eliminate each other on the right-hand side because you have two terms inside that logarithm. You have the natural log of 7 times e to the 5 minus t power. So you can say, well, anytime I have a multiplication inside a logarithm, I can expand that and say, well, it's the natural log of the first term, natural log of 7, plus the natural log of the second term, the natural log of e to the 5 minus t. Now at this point, that natural log and that e are inverse functions and can cancel out. So from this step to this step, all I'm showing is this natural log and this e canceled, and I'm getting the group 5 minus t. But please don't forget that natural log of 7 is still in there. Okay, so now my goal is to solve for t. So I added t to both sides and got an 8t. And I knew I wanted to move all my constants to the right-hand side. But when I move this 5 to the right-hand side, I'd have to subtract it. That's just going to cancel out the 5 that was on the right, leaving the only constant on the right-hand side, the natural log of 7. So you get 8t is the natural log of 7, which means t, and again, they only want the exact answer. T is going to equal the natural log of 7 over 8. And then you can see that that is exactly how I answered it on the Achieve, and it went just fine. I think you'll be pretty good with this section, but if you do run into any problems, please let me know. I'd like to help you out. The next and last section out of this chapter 1 is just going to be mainly making sure you're comfortable using your graphing calculator, both the graphing screen and the table screen on it, and then working a few other just evaluation problems. And then we're off to chapter 2, where we'll start with the definition of a limit and the equation of a tangent line.